This meeting is being recorded.
All right, welcome everyone to another Quantum Matter seminar. It's been a while, and it's a great pleasure to introduce today Elbio Dagotto, who's been here before, and he, as you may know, he's been working for the past couple of years on uh, this new family of potentially high TC superconductors based on nickel instead of copper. And today he's gonna tell us about the latest developments. Please, Elbio, take it away. Thank you for being here with us today.
Okay, no problem, Adrian. Thank you for inviting. Thank you for the presentation. So I will be discussing the new era of nickel oxide high TC superconductors. Together with my name, here you have the way to reach me in case you have comments, critiques, anything you want to send my way. Just use this email and I will do my best to answer. I have a joint appointment between the University of Tennessee at Knoxville and Oak Ridge National Laboratory, ORNL. And this is work that is very kindly supported by the Department of Energy, Office of Science, Basic Energy Sciences, and Materials Sciences and Engineering Division. Usually I have this page towards the end, but I never make it to the end. So I better show my main collaborators early on. So I have many collaborators in this area, but the core are these 5 individuals shown here: Yan Shan, Thomas Meyer, Lin Fan Lin, Adriana Moreo, and Satoshi Okamoto. Especially I want to bring to your attention the 2 big experts that I will be reproducing results of. Yan Shan is our primary ab initio expert, while Thomas is our primary RPA and DCA expert. Just a little warning to the audience. For reasons of time, only a few papers can be cited. I still think that I'm citing 20, 30 papers, but there are hundreds. So if you are unhappy by the way I cited you in my work, simply looking at our publications. There we try to be extremely fair. Often we have over 100 citations per paper. And if not, if you are still not there, send me an email and we will fix it. Okay, so let's start with the physics. High critical temperature superconductors. Well, since superconductivity was found in the copper oxides in the mid-80s, clearly there has been a fascination with high critical temperature superconductivity in the community. Early on, we were selling the story as amazing applications. We were expressing that in the near future, we will have zero resistance cables at room temperature. Well, turns out that more or less in the copper oxides, we are stuck at half the way between the absolute zero and room temperature. We are at 150 Kelvin. But still, from the perspective of fundamental physics, it is a big challenge. The real beauty and driving force is the fundamental physics in this moment. In 2008, we had the second wave of high TC that was based on iron. This is not an oxide. It's the companion of iron is tellurium, selenium, phosphorus, and so on. It's not oxygen. And now I will speak about the nickel oxides. The first big publication was in 2019. I will have one page reminding you of that publication. And then the super frenzy started in 2023, as I will describe along the way in my talk. There are hundreds of papers, so my talk will try to focus on this vast growing field. One observation is that this is a subject that is widely dominated by research done in China. By comparison, there is little research. Little research in the US and in Europe. So one of the purposes of this talk is precisely to try to induce more work in this geographical area. So the first page is the introduction of the early days of nickel-based high TC. After the initial copper-based high TC frenzy, other transition metal oxides were tried. Many were proposed theoretically, but it is only recently that success has been reported. And here is a figure that is very illustrative of the progress made in 2019 in this Nature paper by the group of Harold Juan at Stanford. The story is that on top of one of the canonical substrates, like STO, you can grow a perovskite phase of neodymium nickel oxygen 3. This is the canonical perovskite. Nickel is in gray. The oxygens are 6 oxygens surrounding the nickel in red. And then doing some of the magic that the chemists know how to do, you do an oxygen reduction. The O3 becomes O2, the apical oxygens are gone, and then you end up in the infinite layer phase. It is very difficult to grow this without going through the step of O3. So you collect a thin film of the 112, and turns out that if you measure the resistivity, and if you do a little extra, you dope with strontium. Strontium is in a 2+ valence, neodymium 3+, so you are doping with holes. Turns out that the resistivity shows the presence of a drop to 0 at 15 Kelvin. In bulk samples, we don't have similar results. It's difficult to make the 112. The current record, according to a Nature paper last year, is in this material and is already 40 Kelvin. One of the interesting aspects of the 112 is that nickel happened to be in the 1+ valence, which is very rare. And that corresponds, if you do the counting of electrons and you place them in all the orbitals, that corresponds to a 3D9 configuration, exactly the same as in the copper 2+. So this was the early days. And then the big news came up when superconductivity was reported at 80 Kelvin, that's above the boiling temperature of nitrogen, in a bilayer oxide of nickel. The word bilayer will be repeated multiple times in the talk, is crucial. And in addition, this is at high pressure. That's an inconvenient for experimental progress. But that was what was done in 2023. This came up of the group of Meng Wan in China. And this is the crystal structure. Here you have the two planes that form the bilayer. In blue, you have the nickel. In orange, the oxygens. In gray, the lanthanum. So here you have these two planes. One interesting aspect that was noticed very early on is that if you do the more or less elementary theory, very quickly you find out that the hopping, electronic hopping in between these two nickels is robust. And that means it's slightly larger than the one in plane. Consequently, just studying only one of these planes does not seem to be enough. You have to study the bilayer ensemble. That's a factor 2 to remember. And then there is another factor 2. If you look at the valences, let's start with the valences. Lanthanum is in 3+, oxygen is in 2- as usual. If you do the math, nickel will end up in a fractional valence of 2.5. So we say that it is self-dope. If you do the basic aspects, it always happens that nickel needs these two orbitals, the x square minus y square and the 3c² orbital. So contrary to cuprates, this is a 2-orbital model. So there are two factors too, 2 planes, 2 orbitals. For example, for computational techniques, that's not just a mere factor 4 in the CPU, linearly multiplying. Very often this goes into an exponent. So these materials are a big challenge. Okay, the phase diagram is this one. This is after a lot of refinement. This is not the original phase diagram. It's after a lot of refinement in the samples. This figure still comes from Meng Wang's group. What you have in the horizontal axis is pressure instead of doping, as is canonical for the copper oxides. Here you have the superconducting phase is not a perfect symmetric dome. It has a peak around 20 gigapascal. And there is a region of a strange metallicity. That means that the resistivity is approximately linear with the temperature. And then if you keep on going down with Tc, it becomes Fermi liquid. There is a first order phase transition separating ambient pressure and low pressure from high pressure. And in here, there is a modulation of the spin and charge that is referred to as a spin density wave. I don't know to what extent we can refer to this as the pairing compound, because there is a sharp first order phase transition, but you will see as I go you will be the judge as I go on in the presentation. One important aspect is that at ambient pressure and low pressure, you have this this orthorhombic phase. There is the octahedra is not straight. The nickel oxygen nickel it doesn't form a straight bond, but it is bended into a 168 degree. While at high pressure, you get a straight bond. More specifically, the ambient pressure is orthorhombic, and the high pressure is tetragonal, and that a lot of evidence is accumulating that the tetragonality here that will appear towards the end as well in thin films at ambient pressure. This tetragonality is crucial for superconductivity to appear. Okay, so the samples were improved more and more and more. And then we have in this publication, we have this pretty beautiful plot of resistance versus temperature. Very often you have an onset of the in the resistivity plot that previous experience always tells you that onset will eventually become the true critical temperature, and at some point it truly drops to zero. But most people just focus on the onset, and they call that the Tc. And in this case, it's 66 Kelvin. Under other circumstances, mixing lanthanum with praseodymium, bringing neodymium into the mix. The current record is very close to 100 Kelvin. And you see here this beautiful linearity. The resistivity goes linear with temperature in the normal state. This suggests strong correlation simply by analogy with the copper oxides. At optimal doping, they also have a linear resistivity. At the optimal pressure here is also linear. It's just an analogy. Then I will add the caveat that in the nickel oxides, the magnetism is far from being fully established, mainly because of the absence of large samples for inelastic neutron scattering. So, this is one suggestion of a strong correlation, but there are others that are still missing. Okay, so on the ab initio front, our group was among the first to produce results, but independently others published the same results. So I want to be really fair with the community. There is a lot of overlap in the literature, but it was great to see that other groups were arriving to the same outcomes. The early DFT calculations showed these 4 bands. It's 4 bands because you have in the unit cell, there are a few subtleties, but just in a simplistic way, the unit cell has 2 nickels. Each one has 2 active orbitals. So if you focus on that manifold, then there will be four bands appearing. And here you have the 4 bands. of a special importance is the gamma band that has this whole pocket. You see the Fermi level is at 0. So this band is not fully occupied. And if you focus on the Fermi surface, there is a gamma pocket, as shown here. Well, it turns out this gamma pocket, at least within weak coupling techniques, it plays a key role, to a point that its presence or absence is correlated with the presence or absence of superconductivity. It is that drastic. In a strong coupling, I am not sure the situation is evolving there. So I have here a couple of references from our group and also other references from other groups. These are two very nice reviews that I would like to bring to your attention. With the bands, you can do a fitting, at least in a range of energies, get electronic hoppings, get the crystal field between the two orbitals, construct a model. The other three orbitals of a 3D shell are considered doubly occupied and not included. So, then you can use your best many-body calculation and proceed. You have everybody has all the information. And now, the fact that this top of the gamma band is so close to the Fermi level, it will become an issue because sometimes calculations render this a little bit below. Sometimes experiments themselves are disagreeing on whether it is a little above, a little below. Is that's a matter of debate in the community. And that gamma pocket has a high density of states because of its flatness, so it's important. Anyway, here there is a little bit of repetition compared with the previous page. But if you look at bilayer, I'm recalling that the hopping along the z-axis is the largest. It's not larger by a factor of 100. It's just a little bit larger, but it's sufficiently larger that is prominent. Early on, the notion of a dimer was brought to the attention of the community. Even without including any correlation or anything, you have already at the tie bonding level the bonding anti-bonding states characteristic of a dimer. And this has been the starting point of many theory calculations, starting with the dimer and then building up from there. So these dimers are another major difference from the cuprates. To understand LNO, LNO is the abbreviation for lanthanum 3, nickel 2, oxygen 7. So we need both layers, we need the two orbitals, and we have to remember this concept of dimers that appears to be important. And at this point, say two members of this team, they have research going back in time, and we have studied these bilayers. But from the perspective of a one orbital system, myself and collaborators studied bilayers in the T-shape model, and Thomas Meyer in the one orbital Hubbard model, and we already noticed that there are circumstances in the modeling that lead to Cooper pairs along the z-axis, along this location of the dimers. So this appears to be an important part of the framework. Okay, but what we really did early on, and many other groups did the same, is we studied this Kanamori-Hubbard model. Kanamori-Hubbard model is the Hubbard model supplemented by the Hund coupling. Is the multi-orbital extension of the canonical one-orbital Hubbard model. We use RPA. RPA is random phase approximation. A 10-second reminder, the random phase approximation is if you consider the electron hole, you work in momentum space. If you consider the electron hole bubbles and the dashed line is an interaction, then you pick up a subset of Feynman diagrams. You pick up the ones that you can add up because it's a geometric series, one bubble, two bubbles, three bubbles, and so on, and that generates a pole in the denominator. And that's the famous RPA using nuclear and high energy in condensed matter. And these are the results for the magnetic susceptibility within RPA. 25 and 50 gigapascal, this is using the lattice parameters of the experiments. 0 gigapascal is not. We are assuming tetragonality and then letting the code to fix the lattice constants. So, at high pressure, you already see this little peak. At ambient pressure, it becomes a robust peak. So it would be fantastic to find a way to stabilize the high pressure phase, the one that has the 180-degree bonds, nickel, oxygen, nickel, to stabilize that all the way to ambient pressure. That would be a dream, but it's easy for me to say. So there seems to be activity near pi 0, and of course the rotated one, 0 pi. Other techniques, such as the dynamical cluster approximation, this is a paper of last month, reach similar conclusions. It's a totally different approach, but they reach similar conclusions. And look, the literature is vast. I don't see a lot of disagreement among the theories. This seems to be a robust result. So let me just, for simplicity, bring this peak all the way to X. I know it's shifted, but to give an easy cartoon, I will move it all the way to X, and I will declare that the peak is at pi 0. By doing that, that establishes an analogy with the iron high-TC superconductors that also had a peak at pi 0. In a cartoon of spins up and down, that leads to this very simple cartoon. If it is pi along the x-axis because it is a stagger, and it is 0 along the vertical axis because it is uniform. So you end up with these pluses and minuses in columns, and of course the rotated one, 0 pi. This has not been confirmed experimentally yet. Again, the big problem is the absence of samples large enough, of good quality enough to do inelastic neutron scattering. Other techniques have been used. I will show that in just a minute. By the way, nematicity is possible for the experts of the iron superconductors. You may recall that in that area of research, there was a big effort around the issue of nematicity. You have two possibilities, pi 0 and 0 pi, and there is the possibility that upon cooling, you may go first through an icing transition, breaking the symmetry between these two options, and only later, at a subsequent critical temperature, you may end up with the true long-range order. So that was widely discussed for the iron superconductors. For the nickels, I'm aware of only one paper on the subject, but this is an avenue of research that is widely open for whoever wants to explore it. Okay, experiments. As I said, the samples are tiny, not of great quality. This reminds me of the early days of the copper oxides. In the early days of the copper oxides, in spite of the fact that every year the crystal growers were saying that their samples were fantastic compared to the previous year, the statement was repeated the other year, and it continued and continued and continued. And some sort of convergence was found after at least 7, 8 years. That was when the D-wave character was finally unveiled. So quite likely there is a long way to go before we get great samples and consequently very robust experimental results. Anyway, RIGS can be done because it's surface sensitive. In this publication, in Nature Communications, the results were interpreted using diagonal stripes. This is the interpretation given in this paper. There were two stripes shown in that paper. I'm showing one, the simplest one. So they call it double stripes because red means a spin down, and here you have a stripe along this diagonal, and then there is another one next to it, and the same for the spin up. Now, this cryptic comment here is because time ago, the fashionable area of research was the manganites, and in that context, when you saw structures like this, you didn't think of a double stripe. You thought of a zigzag chain, because if you look at the hoppings are much stronger nearest neighbors than along the diagonal of the plaquette. So given that circumstance, it is more natural to think of the red here as going in a zigzag pattern, and that is called the E phase in the area of manganese, as per the convention established by John Goodenough long time ago. So and also let me remind you that ambient pressure has a lattice distortion. High pressure doesn't. So they may display different magnetic tendencies. And this is a figure that I extracted from this publication here. It's quite interesting. In this figure, you have at ambient pressure, you have short bonds and long bonds in the distorted atomic arrangement. And if you look, for example, at the green bonds, they also form a zigzag pattern, exactly as the ones I showed you before in the other figure at the top. Okay, they are rotated by 90 degrees, but it's the same. So, from my perspective, there is a possibility that the lattice may be cooperating with the magnetism in producing these double stripes. And then if we were able to stabilize the high pressure phase, then it would go from double stripes to the single stripe. So the summary is the following. Experimentally, and within rigs, it appears to be double stripes. Theoretically, and within RPA, it seems to be single stripes, horizontal or vertical. The double stripes also come in two varieties, one diagonal or the other diagonal. So that's the situation. There is also MUSR, NMR experiments that report a moment for nickel of this value in Bohr magnetons. Well, it was too complicated for me to just look at one nickel in isolation. Remember that it is self-dope. So you cannot just take one ion and more or less estimate the magnetic moment. So I consulted our overlord, Google AI, and according to Google AI, the maximum magnetic moment for this material, for nickel, would be 1.32 Bohr magnetons. So it is about what, 20% of the maximum. Is reasonable, is compatible with other materials. But still, the robust antiferromagnetism of this kind is missing experimentally from neutrons to make a final case for a strong correlation. In my book, you really have to see the magnetism before declaring that it's strongly correlated, magnetically driven. I'm trying to be very, very honest here in the presentation. Still within RPA, you can plug this magnetic susceptibility into formulas of RPA, deduce what is a dominant pairing channel. And turns out that the S plus minus is the dominant pairing channel. Well, there are many words in this page, but this is what you have to remember. This is the Fermi surface, the same one I showed you before, the gamma pocket, the beta and alpha sheets. But you see two colors now. They represent the superconducting order parameter. For example, blue means negative and orange means positive. And under a rotation of pi over 2 is invariant, so it's an S wave. According to the irreducible representations of the square lattice, but also it contains two signs. So we call this S plus minus. This is the same notation as used for the iron superconductors. And in those days, there were many experimental techniques that once you have good samples, you can employ. For example, there is a resonance in neutrons that was predicted because of a non-trivial arrangement of the pluses and minuses, and it was confirmed experimentally. So we badly need good large samples in this area to keep on moving forward. So this is a summary for the bilayer nickel oxides at high pressure. And next, I will switch to the thin films. So in this publication of ours, we had this sketch. If you have not been, if you connected late or have been distracted by your phone, this is a nice sketch to remember as a summary of the first half of my presentation. On the left, you have the nickel oxides. On the right, the copper oxides. LNO seems to have, in the bilayers, seems to have an orbital C square that is playing a very prominent role. The other one is not to be neglected, but we are thinking about starting with just one orbital, the 3C square. In that MPJ quantum material of a month ago, that was by our team. Look at the abstract. There is a possibility that we can get away with just one orbital. Of course, it will not be quantitative, it will be only qualitative, but never mind. The cartoon here does not intend to put down the x squared minus y squared orbital. And this is RPA giving an S plus minus. For the bilayers of copper oxides, the famous BISCO, always the x squared minus y squared is dominant. By the way, the two colors, the bluish and yellowish, are the two signs in the wave function, right? So the x squared minus y squared dominates. The hopping between these two is negligible, basically. It is widely accepted that you get a D wave. Upon a rotation, you collect a minus sign. This is why it is D, and the blue dots represent the node. This has been well established within angular resolved photoemission. So that's the difference between the two. Just to complete the picture, why these gamma pockets are so important within RPA? Well, it turns out that there is some degree of nesting. It's not super nesting like in the nearest neighbor one orbital Hubbard model. We have a tremendous amount of nesting. Here is more reduced. For example, this portion of the gamma pocket is separated from this portion of the beta sheet by a vector that is approximately pi in the canonical units. And then you have all the other possibilities, right? It's this one with this one, and so on and so forth. That gives enough nesting to boost the pairing. At ambient pressure, where there are no gamma pockets, experimentally, this is the result. If you look at this publication, they write very clearly that the beta and alpha sheets are fully confirmed by angular resolved photoemission. So that's at ambient pressure. So, there is, so far, there is a good consistency among the theories, among the experimentalists. So the community is getting together in this field. So it's quite interesting. I'm about to switch to thin films. If there is any question about the high pressure, this is a good moment to formulate it. Otherwise, I continue with the most recent developments, which are last year and this year. Okay, so I continue. So the big development in 2025 started with these two publications. The one at the top is from Stanford. The one at the bottom is from China. Both of them in the title they say ambient pressure superconductivity, and they have obtained superconductivity in ultra thin films. That's the big news. The strain that works is compressive strain. There is a cartoon representing the fact that the A and B lattice parameters are being contracted. Consequently, the other one is expanded. The two typical techniques to make these thin films have been employed widely. And this figure comes from the paper at the top, Ko et al., resistivity versus temperature for 3 different substrates. The one that works is SLAO. And here you have the complete formula: strontium, lanthanum, aluminum, oxygen 4. And this provides a compressive strain of -2%. The minus means compressing, and 2% is the change in the lattice spacing. Okay, it may seem little, but all of us that have done estimation, for example, of hopping amplitudes, these wave functions are localized and rapidly decaying with distance. So a 2% change can be quite robust. And the other lattice constant adjusts by itself. So here you have the onset, and in this inset you have the drop to a zero resistance, so that there is no doubt that the onset is created by superconductivity. So this is a nice sketch, a nice cartoon that appeared in this communication physics, showing the bulk number for 3 to 7 for the lattice spacing, and if you go to the right, is tensile. It is expanding. If you go to the left, it is compressive. So it is in this portion that we get superconductivity. There is a detail that is really interesting. As you go with a compressive strain, the atoms rearrange themselves and they go into the FMMM phase, which is the same that is stabilized at high pressure in larger samples. That was at the beginning, the first half of my talk. So everything is self-consistent. It appears that the thin films, due to the influence of the strain, transform their atomic arrangement from the distorted orthorhombic into the tetragonal phase. And that's the fertile ground for superconductivity. And you can consult these 2 publications from the theory perspective that arrive to the same conclusion using ab initio techniques. So tetragonality is crucial. Okay, well, there have been who knows how many papers on the topic since the 2 first ones. So I'm going all the way to the end of 2025. In December, this paper appeared in the arXiv with a record TC of 63 Kelvin for thin films. This is in a mixture of lanthanum and praseodymium. That's a little mysterious for the theorists, but the experimentalists, they seem to have converged to the notion that a partial replacement of lanthanum by praseodymium somehow makes for better samples. Don't ask me why, but this is in practice, this is what happens. So they love to intermix these 2 elements. Both of them are in a 3+ valence. And here is the resistivity plot. The onset is at 63. Eventually, the drop occurs at between 40 and 30, but the onset is what matters. And there you have again the linear resistivity. It's quite remarkable that we see this strange metal behavior for whatever you're doing. When the TC is the maximum, it has a linear resistivity. You will see that in just seconds. So I was saying that you have a strange metal behavior with a slope 1 in the plot rho versus temperature. The lattice constant, this is the difference between thin films and high pressure. the lattice constant along the axis perpendicular to the interface is expanding under strain, while for the hydrostatic pressure of the early days is contracting. The hydrostatic pressure reduces A, B, and C. The strain compressive reduces A and B and expands the last one. So this is another knob to play with within theory. It's quite interesting that we have this extra degree of freedom, and this story will come back very soon when I discuss the channel of pairing. I give you an anticipation of what I'm about to show you. The S and the D wave channel are very close in energy. And maybe playing with this number, we may go from one to the other. I will talk about that. Before that, a recent development. You see many things are happening. You blink and something important happened in this field. February, we got a paper in Advanced Materials where for the first time another substrate was used, lanthanum aluminum oxygen 3. This is the only paper that we have, to my best knowledge, using this different substrate. Now the compression is smaller. The claim is that with less compression, maybe you can grow thin films thicker than with a high compression. But the TC is only 10 Kelvin. So that's the status of this area. And here this is a figure taken from the same reference, the one of December, but they collected a wide variety of samples. They play, for example, with the ratio lanthanum praseodymium. They produced 90 different samples, and they found a correlation between the critical temperature that is in the horizontal axis and the exponent and the power of the relation rho versus temperature, resistivity versus temperature. And it's very obvious to the eye that as the TC goes down from left to right, you see a clear curvature above the TC. This is more quadratic. Here is linear. So from simply visual inspection, you also conclude that the lower the TC, the higher the chances that you will get something looking like a Fermi liquid. And the same happening at high pressure. You remember I showed you that distorted superconducting phase. It had the strange metal where the TC was high, and then as the TC went down and down, all the way to 90 gigapascal, the Fermi liquid appeared there. So these are interesting aspects. Now I will start with portions that are, this field is so new. Results are appearing left and right from theory and experiments that at this point, I would start with presenting to you results that are not necessarily accepted by the entire community. And I will say it with clarity when that happens. So let me start with this publication. The blue is the reference. This was ARPES, now with the possibility of dealing with thin films at ambient pressure. We can do ARPES because ARPES is surface sensitive, doesn't need a bulk sample. So they studied one unit cell film of this compound. I still call it the 327 on the canonical substrate. And this sketch here is an abstraction done by the experimentalists of a lot of results that they collected. It looks like a theories plot, but it's not. This is from the experimental group. And they report an alpha and beta sheets as everybody does, and also the gamma pocket. So at that point, everything appears to be compatible. You need the gamma pocket to go superconducting. It's great. So this thin film is superconducting. But there is but there is a controversy. So the issue is from where comes. So they did, together with the ARPES, they did some DFT plus U calculations, and they noticed that in order to match the size of the gamma pocket, they needed some extra hole doping. Otherwise, the gamma pocket was too small. So they added hole doping, and at that point, they blamed the possibility of a strontium migration from the substrate to the sample. The strontium is part of the substrate. There is a possibility, why not, that at the interface between this material and this material, you may get a partial replacement of lanthanum or praseodymium by strontium. They have different valencies that would correspond to hole doping. But there is a controversy in the literature, and I'm connected with many experts that send me emails. I know that this topic of the strontium migration from the substrate to the sample is still controversial. Some are in favor, others are not. So this is a situation evolving. We don't have the final answer yet. And there is more. While these experiments using ARPES show the gamma pocket, okay, they had to tune with doping the size of the gamma pocket, but they already saw it early on in their theory component. Turns out that there are ARPES experiments that find the gamma pocket 70 MeV below the Fermi level. So we are in a paradoxical situation here, using the same technique, seemingly the same technique, different samples, of course. Each group has its own sample. You either have the gamma pocket slightly above Fermi level or slightly below, right? So, and sometimes the signals are too weak. And we also have this issue that is a bit annoying, that is because of the matrix elements that appear in photoemission, it depends on the energy of the incoming photons. They are, I don't know, 200 EVs or so, and you can regulate that. Depending on the energy and the matrix elements, you can unveil different portions of the Fermi surface using different incoming energies. Consequently, you have to be astute and getting several incoming energies to get the full picture. So it's a complicated matter. Okay, so that is the experimental status. And now I will talk in the last 10 minutes on our theory work on the nickel oxide interfaces. I'm emphasizing by our team here because other theory groups do not agree. Specifically regarding the channel. We are concluding, and I will show you the evidence within our calculations, that for the interfaces, we are finding a dominance of the D channel, while other theory groups, in seemingly a similar environment, they find a dominance of the same S plus minus as before. So I just tell you what we did. We consider a thin film with a 1 unit cell. For the benefit of the audience, let me also give you a little warning in the language used. Turns out that the atomic arrangement of the nickels has this extremely annoying feature by which you have a bilayer here, one plane, the other plane, and then the other two on top are shifted by half a lattice spacing. Consequently, the true unit cell involves 4 nickel oxygen 2 planes, as opposed to only 2. But they are very weakly coupled anyway. But to be very strict, 1 unit cell involves 4 of these. It's different from 1 single bilayer. Many theories just study 1 single bilayer. Well, Not necessarily the results are the same. If you study one single bilayer, ultra super thin film, as opposed to one entire unit cell. It's one of those annoying details that are complicating the literature. Then in this slab geometry, you add about 20 angstroms of vacuum, and you plug that into the codes for ab initio. So essentially, this structure goes repeated periodically. That's a way to simulate an interface. Just to add more entropy, in the thin films, you can do ARPES, you can do STM, looking at the local density of states. And once again, there is some disagreement among the experimentalists as well. Some report a match with D wave, and others report a match with S wave. Photoemissions, some photoemissions claim to find a node, others say no, there is a gap all over the place. So the field is evolving, as it happened in the copper oxides. So we're still not converged yet. But this disagreement may be caused by something intrinsic. In what we do, in what other theories do, we find the D and S channels of pairing to be very close in energy. This is something that we already observe in the area of bilayers of the one orbital Hubbard model. If you happen to be, so there is a transition between the D wave of one plane into an S wave, plus minus, of the bilayer when the hopping is robust. So if nature has placed this material close to that switch in place, then it could be that different geometries, small details, may unveil different channels, right? DS appears to be always S plus minus. Even within the D, there is some disagreement. It can be X squared minus Y squared, or it can be XY. So it's evolving. So I tell you what we found. When I say this is work by our team, I'm talking about a preprint that was placed in the arXiv in December, and now we are going through the standard carousel of referees. So this is with high pressure, you are contracted in all directions. With compressive strain, you are contracted in two directions, expanded in the other one. And within RPA, we get the S plus minus. I already explained this several times. Within our calculations in the framework I just described, we are finding dx squared minus y squared for a small amount of doping, let's say 6-7%. This is what we find. It's the same Fermi surface, of course. The distribution of pluses and minuses is as shown in this sketch, and you have nodes in the pink dots. You have nodes because this is a D-wave superconductor. So my aim is to give you a true overview of the field. So this is what we find. Other groups disagree. Other groups find a more compact result. They find S plus minus in both cases. So we will see. But if we happen to be right, that would be really quite interesting. It would be the same material displaying different pairing channels depending on the experimental circumstances. So high pressure could lead to S plus minus. Ultra thin films under compressive strain will lead to D wave. That's quite interesting. So just to finish our calculations, so I'm showing here on the left, I'm showing what we did for the undoped case. This will show you how subtle this story is. For the undoped case, we have the gamma band just 10 MeV below the Fermi level. This is within the canonical DFT. Now, to be honest, how can we or anybody else claim that we have an accuracy of 10 MeV? This is what simply I'm reporting what the computer tells you, but nobody has such an accuracy in a many-body problem where the energy scales are in the EV range. The bandwidth is about 3 electron volt. So, and the U, according to constraint RPA, is also of the same magnitude, 3 electron volt. It's too much to ask for a few MeVs precision. But what we did, the undope doesn't contain the gamma pockets. You need to hold dope to get an area of gamma pocket compatible with the photoemission, at least with the photoemission I cited. That goes into about 6% doping. So, but there are theoretic works by many other groups. Please visit the literature corresponding to this. Is just a subset of the many theories that have produced publications in this area. And this is what we got within RPA for the pairing strength, lambda, for different channels. So you see at 3 is the undope. That 3 goes all the way from the early portion of the presentation. We had the 2 nickels, we had the 2 orbitals per nickel, and we did the counting. The valence 2.5 plus corresponds to 3 electrons. So this filling means 3 electrons in the 2 nickel unit cell. Nothing happens, right? Remember that we have A and B contracted, C expanded. And then with about 6% doping or so, the X squared minus Y squared channel becomes very prominent. And eventually there is a switch to the XY, right? Now we are asking ourselves, and colleagues have asked, why this switch from one to the other? This is a tentative answer. It's moving my hands only. But remember that I mentioned to you the concept of dimers as playing a very important role, because the hopping in between the layers in the bilayer was robust. But because in the compressive arrangement of the ultra-thin films, the C is expanding, that hopping is reduced. Well, you see that can affect the channel of superconductivity. So we blame a weakened interlayer hopping caused by the increase in the lattice space in C for the switch from S to D in our calculations. So look, we're not sure if we are right, but if we are right, this is something qualitatively quite charming, to have different pairing channels under different, basically geometric circumstances. So anyway, I arrived right on time. I arrived to the summary. So the new era of nickel-based high TC has started. For the cuprates, it is well established that from the modeling perspective, you need one orbital, the famous dx squared minus y squared. It is a strong coupling. We have a robust antiferromagnetism. There are good and shiny single crystals. You can do inelastic neutron scattering. Everything is fantastic. We still don't agree with the theory, but at least the experimental portion is very robust. And the TC, the record TC, is at 150 Kelvin if you push it a little with high pressure. Nickelates. This is a new field. Surely we have 2 orbitals that are active. And already at the level of magnetism, there is hesitation. Stripes appear to dominate from the RIGS and from the RPA perspective, sometimes diagonally, sometimes horizontally, but it's a stripy environment. Do we have a strong coupling? Well, we have a linear resistivity. Magnetism, because of the quality of the samples, is still not strongly manifested, so we don't know. So we cannot declare that this is strongly correlated. Calculations that claim to be able to estimate the Hubbard U, they place that at the same range of the bandwidth. So that would be sort of intermediate coupling. We need pressure, either real pressure or strain pressure. And the record TC, as of October 14, there was a publication in the arXiv reporting a TC of 100 Kelvin. So 100 Kelvin, is not too far from the 150. So the only place to go for this TC is up. So this is getting more and more exciting. And then we have this also a discrepancy between the S plus minus channel or the D wave channel, right? Anyway, this is a fast evolving situation. You notice that I cited publications of December, February 26. It's changing very fast, and I'm pretty sure the best is yet to come. Okay, with that, I end the presentation, and I'm open to any question you may have. Thank you.
Thank you, Elbio, for a very nice talk. This session is now open for questions. If you're in the audience, please feel free to unmute yourself and ask directly. Otherwise, you can post the question on the chat.
I have a question.
Yes.
So did you try? I saw that you have these two channels, d x y and x squared minus y squared, quite close. I mean that they compete. Did you try d plus id?
Oh, excellent question. Excellent question. I have received this question before. Within mean field approximations, every time you have two competing channels of superconductivity, you may end up mixing them with an imaginary unit. So it could be dx squared minus y squared plus I dxy, or even before that, it could be s plus minus plus I d. So I have received this question many times, and we don't have an evidence of that. Within mean field, very likely that will be the outcome. But we ourselves don't have an evidence of that. And I consulted with my colleagues of the early days of bilayers. Remember that I mentioned the one orbital case. The bilayers were studied. So in that case also, you are transitioning from D wave when you have the two planes. When one plane dominates, you are D wave. When the coupling becomes strong between the planes, you go S wave. You could also see that. And talking with the experts in computational approaches, they claim not to see any evidence of a mixing of the form S plus ID. Look, all techniques have restrictions. Who has the perfect many-body approach? Nobody. But this question is very real. It's very frequent. If you have two pairing channels competing, why not mixing them, creating a region of that complex number mixing, as opposed to just dealing with a sharp first order phase transition? It's too early to say. Sorry, but it's a very good question that I receive frequently.
Okay, thank you. Very nice talk.
Thank you.
Yang Yu, please go ahead.
Yeah, thank you for the nice talk. I have a question. According to my understanding, you have two sets of RPA calculation. One is for the bulk with high pressure. The other is for thin film. It looks like that for thin film, you actually consider 4-layer, and for bulk, I think it's 2-layer periodically. Is that correct? So if it is correct, it seems that the two set of calculation not only different from each other by C, but also by the calculation setting. Am I correct?
That's an excellent question, and it is so embarrassing that I don't know very well the answer. But I think in the crystal structure that I consider very early on, you see that this is what is plugged into the DFT calculations. And here you have the two nickels of the bilayer that I emphasize. But if you look at the plane at the top and bottom is the next bilayer, the nickels are shifted. So presumably, look, I will ask my collaborators, but presumably at high pressure within DFT, we did the right thing of having the four planes. The coupling between them is supposed to be weak. It's just that, to me, it's just an annoyance that we have this shift of half a lattice spacing. Frankly, it cannot change so much the concepts, but it can change the position of the gamma band, which is so close below or above the Fermi level. So these tiny details that conceptually should not matter too much matter if your focus is on the gamma pocket. So the answer to your question is, apparently, based on this plot, we have done the calculation with a unit cell involving four planes, both at high pressure and in the ultra thin films. So, or at least I hope this is what we did.
Yeah, I see. Thank you. Yeah.
No problem. No problem. Thank you for the question.
I have a naive question. Is it obvious that the pairing glue is somehow driven by magnetic fluctuations in these kind of materials?
Obvious is not. You see, there is this, what's the name? There is the community of electron phonon BCS. It's embarrassing that I don't remember the precise name, but there is I think a Macmillan upper limit that is universally accepted, and it is in the range of 40 Kelvin or so. So when you see numbers for the TCs of 80 and now mutating into 100, and then you know the natural tendency is to say that this cannot be phononic. Now, is that a mathematical perfect theorem? No, not at all. It's just the early estimations when everybody was convinced that superconductivity could only arise from electron phonon coupling at a BCS. That was approximately the top that they were expecting. So no, it's not obvious. Also, there is a possibility of a coupling between the magnetism and the phonons. Remember these photomission experiments by the group of CX Shen at Stanford, they always talk about this, what's the name? I'm also forgetting that, but they have some areas of the bands that they see experimentally that have like an anomalous behavior. And they believe that is caused by phonons. So maybe these two things are very coupled with one another. The issue is who's the driver and who's the passenger. So it's too early to say, but the analogies with the copper oxides make me believe that the nickel oxides are in the same family. Now, having said that, are we really sure that the copper oxides are driven by magnetism? I hope so, right? Many theorists have invested their entire life assuming that. That would be very cruel if 1 week before passing, someone finds out that it was all a mirage and it's all phononic. If that happens, and I am in my deathbed, don't tell me, okay? I don't want to know. I don't want to know. But look, there is no Nobel Prize for theory of high TC. There are Nobel Prizes for all kinds of things. But in high TC, that it is really reasonable to believe that is the topic that has collected most citations ever. We have the early Nobel Prize for Bednorz and Mueller and nothing else. So there seems to be still some doubts and disagreement in the community. I am in favor of the magnetic pairing. I can see that in some of the calculations I do. Very early on, when I was a young postdoc, I already found the way superconductivity in these exact diagonalizations calculations. In those days, nobody was talking about the wave, but it emerged from the calculations, and a few years after it was widely accepted. So I don't have any reason to be suspicious of this mechanism. One aspect that worries me a little bit is the issue of retardation. In the BCS theory, the fact that the attraction is time delay because of the big difference in masses between the protons and the electrons, you can envision that one electron is followed by the other one in the Cooper pair at substantial distance, so that the repulsion is overcome by this weak attraction. In everything done in the area of magnetism, the Cooper pairs are substantially smaller in size. So the issue of retardation is something that worries me in the back of my mind. The Cooper pairs cannot be that small. So we still have a lot of work to do. But now everybody's shifting to AI and machine learning. So we have so many areas of research that we have focused extensively, we didn't solve, and then we move on to something else. It's annoying, but it is what it is.
There's a question from Johannes. Please go ahead. Johannes Nogelein, you have your hand up. Please go ahead and unmute yourself. We cannot hear you. Okay. I don't know what happened to Johannes, but do you have any other questions from the audience? All right. If not, we thank Elbio one more time for a wonderful talk and sharing his results with us. And we'll meet again sometime in the future with another for another quantum matter seminar. Thank you everyone for joining us today.
Thank you. Thank you.
Bye.